Thank you very much. So I will introduce myself. My name is Tomáš Sedláček. I come from Czech Republic. Currently, I work for a company DataDo. And I'm pretty surprised there is so many of you. Can I take a selfie with you just to prove my boss that I am not at the vacation by the sea? I need some evidence, you know. Are you enjoying the conference so far? Thank you. And today, I'm gonna talk about PGQ. What the PGQ is, I will talk later, but PG, you may know that it's abbreviation for Postgres. Q is the queue. So PGQ, Postgres queues. But first, a few words about DataDo. DataDo is a company where I work, and we do the data. We extract data, transform it, load it. We connect to various databases, file storages, databases, HTTP files, REST APIs. We do whatever with the data in the Go applications, and all of our applications are running in AWS. So we deal with some jobs, extractions, which may take milliseconds to seconds to minutes. So we have the context why we have the queues in there, but I will be more concrete later. So this is the queue. Probably you have experience being in some queue already, at least before the lunch today. So this is the Prague Castle worth of visiting if you have never been to Prague yet. And behind the gate, there will be probably some guard doing some security checks. And why the people organized in the queue, it's quite obvious, because if the queue was not there, all the people walked in. If it is a Node.js guard, it would probably say, error, too many requests, I'm quitting. But fortunately, people organized in the queue, so the guard can do the security checks according to its needs. In the computer world, the queues are there with us, like the system of the queues and the principles of the queues are for decades. It's there since the beginning. And nowadays, there are a lot of scenarios why you can use the queues for. For instance, the communication channel. You can use queues as a channel for communication between your services written in Go, written in Node.js, written in Rust, whatever language it is. It can be used kind of protocol to communicate between the services. You can use it for task scheduling. You can use it for asynchronous communication. You just pass, or some service just passes some request to the queue, and later on, some other service or itself can process it. It can be used very easily for load balancing to keep your services protected against the overwhelming, like the Node.js got too many request error. You can use it for throttling, rate limiting, and I believe, because we are a lot of people in here, if we put our heads together, we could name a lot of scenarios and use cases where you could use queues. And because it's quite common pattern, there is already a lot of message queue systems. Sometimes they are called message brokers. To name some, the open source ones, one of the most popular is RabbitMQ. There is Apache Kafka, Apache ActiveMQ, NATS. Each cloud provider has some own implementation of the queues on their own, so there is plenty of them. Redis, there was a talk about Redis on this GoLab, so Redis as well, you can use for PubSub communication. Just out of curiosity, is there any one of you who have some experience with RabbitMQ? Please raise your hands. How many of you? Quite a lot. Kafka. The birds are more frequent. NATS. Okay. Redis, I believe all of you are users in some way. I will skip the Amazon, Google Cloud, and so on, but has anyone of you have the experience with Postgres? Not for queues, but altogether. Okay, so almost everyone. Nice. So there comes the PGQ. The PGQ is the open source Go package that we created in DataDo. Basically, we created means that my colleague Tom created it. And it's implementation of the queues on top of the Postgres. It uses regular SQL statements, so if you know SQL, you are ready to go and use it. It's, at least from my point of view, reliable and easily observable. I will show you in the demo later. And the package itself you can find in godata.com. Yep. If you don't know. And it contains the basic consumer and publisher implementations. When to pick PGQ if you want to build resilient systems because it's built on Postgres. The biggest advantage when to use it is when you already have Postgres in your stack and you don't want to administer another technology like Kafka. Those of you who are running Kafka probably know that it's not a simple task to manage the cluster of Kafka. And if you want to get the observability by default by using this tool, you can, because it's Postgres. I will show you later. And when to not use it, when you have some specific configurations and needs, when you are transferring a lot of big rates of data, there are probably better tools than PGQ. But in our case, in DataDo, I will show you what we use it for, and we are just fine with Postgres. So to sum it up, why to use it? Because Postgres just works. All of you, mainly or mostly, have some experience with Postgres, so maybe you can vote for me that Postgres just works, that it's very nicely scalable and performant. You all know probably SQL, so there is nothing new for you to learn if you hop on using PGQ. And the main reason from my point of view is that your technology stack will keep simple. So if you don't need to involve any message broker, which was listed above, in order to achieve some benefits of using the queue. And of course, it's no magic. As I will show you, the PGQ is no magic. You can implement it on your own. It's just a bunch of functions that, of course, you are capable of doing on your own, but why would you? Because we are maintaining it. You can participate. You are very welcome if you want to put your hand on our work. And if you are implementing it on your own, you will have to deal with reconnect, timeouts, deadlocks, etc., which is already solved by PGQ. As one wise man who was in this conference said, keep it simple until you can't. So keep it simple until you can't. So don't involve any new technology until you really need it. Where do we use it in DataDo? Just to wrap it, starting from the lower line, we use it, or we operate Postgres as a managed service in AWS RDS cluster. This one is the smallest one which is available, and it is powering our production. And if we could get the 4 times smaller, it would still be sufficient, but unfortunately, AWS offers this as the smallest one we can get, so we use it. And we use it for long duration jobs, like jobs for extracting the data, writing the data somewhere, processing the data, doing the transformation, which these jobs can take milliseconds, but sometimes even hours. But we use it for messages and jobs like sending emails, which are quite fast, saving the customer logs or some logs that we treat in a special way, which are not just the logs that we never see, but logs that our customers can see. We use it as a communication protocol or a communication tool between our PHP applications and Go applications. So we have consumers both in Go and PHP, and they can communicate with each other. And last but not least, we use it for the monitoring. We have built our own monitoring tool just by doing SQL queries, and we know exactly what is going on in our platform, whether the queues are growing, getting bigger, or by this information, we can very easily know whether the consumers are operating as expected or not. So what is under the hood? In the PGQ, the queue is just a Postgres table, the simple table you can create by this command. Don't worry, this command is generated for you by the PGQ if you run the generate table function. I will show you in the demo. And the table consists of several fields. Each message or each row in the table is the message from the queue perspective. So it has some basic identifier, ID of the message, when the field when it was created, When started at means when the consumer started consuming the message, means processing it. There is the information about the log in order to prevent duplicate processing. There is the information when the consumer has processed the message, either successfully or unsuccessfully. If there is any error, it will be stored in the error detail field. And of course, each message contains some payload, which is basically JSON, and the metadata that both sides should understand, like publisher and the consumer on the other side. And of course, there must be some index in order to consumer query to be effective and fast. The message itself, as I said, is just a single record in the database. So if you know Postgres, and majority of you have experience already with Postgres, nothing new. Just the message is the row in the table. And the message has the payload and the metadata that you can read. Publisher, on one side, some application wants to be something to be done for it. So it's producing the jobs for another services usually. So how to create publisher using PGQ? You need the Postgres connection opened. We use standard SQL connection. It can be Postgres or PGX or whatever. Then we create a new publisher passing the DB into it. We compose the payload, which is the JSON, and we create a new message, the message struct. The first parameter are the metadata, which are optional, and the second is the payload itself. When the message is created, we can publish it to the queue of our interest. The queue, the my queue, is the name of the table, name of the queue. That's it. This was the publisher, but you can use it. You don't have to use it. It's just you can do the regular insert statement in your base script, whatever, insert it manually using PSQL or whatever. Everyone who can insert into the database can act like the publisher. On the other side of the queue, there are the consumers, subscribers, or processors. I call it consumer in this talk. And the consumer, it should know how to process the message, how to handle it. So at first, you need, in order to use PGQ, you need to implement the handle message interface instruct that you create. So let's say you create the handler struct, and it implements this message. You get the context as the first parameter. So by passing context, you can achieve the grace of shutdown or cancellation of the processing of the message if the application determines to do so. And you get the message itself from the consumer. And now, after you have this information, you do whatever processing you want. You can call your APIs, you can contact your databases, do every work you need to do. And in the end, you just return whether you processed the message and if it ended with error or not. So usually, when everything goes well, you return process true, error nil, and that's it. When we have the handler, the creation of the consumer itself is quite straightforward. Again, we need the database connection. We pass it to the consumer, the new consumer function. We pass the name of the queue we want to consume, and we pass the pointer to the handler. And at the end, we just say, consumer, run now. And for each message, it is there in the queue, your processor or your handler will be called. This is the life cycle of the consumer. So at the beginning, when you hit run, it tries to find a message, any message to process in the queue, which has not been processed yet and is not locked. If it finds some, it will process it using your handler, updates it according to what you returned in the handler function, and then loops again until there is something in the queue. When there is nothing, everything was processed, it will idle for some short time that you can configure. So it's polling the database to get the new jobs. So what is behind the query, how to get the new messages to process? So this is the whole query that is powering the consumer. I will start from the middle. So we are selecting from the table, from our queue, the messages which are not locked by other consumers and has not been processed yet. And we get, usually by default, we get the one. So we have the ID of the message, and then we update it using the in trunk section. We put the lock to that message, we put the started date field to the current timestamp, and we return to the consumer the message ID, payload, and metadata, which consumer will get, will compose the message struct, which will be then passed to your handler. In order this can work in Postgres, this line is crucial. For update skip locked. It was not there before version 13, if I'm not mistaken. So this is the reason why this concept of queues on top of the Postgres couldn't be used, because this line guarantees that there will be no conflicts between the consumers. It will keep your transactions and transaction of the consumers safe from concurrent processing of the same messages in the queue. Thanks to this, for update skip locked, the whole concept of PGQ can work. So if you want to see how it breaks, you can try it on your own as well. There is a repository, github.com/datado/pgq demo. You can clone it if you want, but I will show it on the screen the same. One prerequisite that is required in order to run the demo is having the Docker, because I am using the Postgres from Docker. But if you have some Postgres instance running somewhere, you can try connecting to it. But you can use the Docker ones. So I'll switch the window somehow. OK. So first of all, I'll just check that there's no Docker container running. OK. If you clone the repository, there is a make file. Make file contains these targets. I will use them in order to speed up the demo. But the first one I will use is make Postgres, which will just basically run docker run Postgres, blah, blah, blah. So I will have Postgres running. And I can do it right now. Make Postgres. It should start the container with Postgres, which is running already. Now we can have a look what make setup does. So I will open setup, and I will see that it just opens or runs the build and runs my setup program, which accepts some Postgres parameter and the queue name. Let's have a look what it does, because there will be the code for generation of the queue. So setup main go, and here I'm just accepting the parameters from the make file. And in order to set up the PGQ, there is a schema package in the PGQ, where I call generate create table query, passing the queue name, in this case demo queue. And if it does not panic, it ends that queue setup completed, which means I will have the queue ready in my Postgres. I'll change something. OK, so let's run make setup. After a while, if I open some viewing tool to my database, I will not see this, but if I run select demo queue, the demo queue exists, but it's empty, obviously, because I just ran create table my demo queue. OK, so in order to publish some messages to the queue, there is make publish command that I will run. But first, have a look what it does. So make publisher, it does. And again, it accepts the Postgres DSN, the queue name, the number of messages I want to publish, some max weight, which is the random number from 0 to 10. I will describe later why it is there. And I will iterate for the number of messages I want to publish, and I will call the publish message, which basically I have consumer already instantiated. So I will create a new message, composing the payload, which is some on the example JSON with random sleep integer value as a parameter. And in the end, I'll just call publisher, publish, and passing the message and the queue name to it. The publisher was created just by this line. OK, when I hit make publish, it should publish 50 messages to my queue. I can verify very quickly by looking at the queue that something is there. There are 50 messages. All of them have some creation day, but none of them has been started to be executed because there is no consumer yet. So no message could be processed either. Let's change it. But before I do it, I will just just run make monitor, which does some queries in the background and saving the results to the CSV file, which we can have a look later. And every 2 seconds, it runs the 3 queries to my Postgres database, and it will check how many messages are there waiting to be processed, how many messages are currently being processed, and how many messages has failed during the processing. I will keep running this in the background. If I'm not mistaken, I can right now show you the consumer, how it looks like. I have 2 consumers ready for the demo. One of them is very simple, so let's have a look on it. And what it does, again, it accepts some configurations like connection to the Postgres, it tries to connect, then I create the handler in here, which is the handler with worker inside. I will scroll down later, and I create a new consumer with passing the DBQ and the handler pointer, and then I just run consumer run. And handler looks like this. It must implement the handler message interface. In this demo case, I don't use context, but I just used message, which I try to unmarshal the JSON from the payload to some structure called job, which is here. It's just ID, which has just ID and the sleep, number of seconds to sleep. And it calls worker passing the job. Here, there can be whatever your implementation needs. But in the end, you just return whether you process it, whether there is some error, or Boolean true, whether it was okay with no error. And the worker itself looks like this. It accepts the jobs. It sleeps for the number of seconds that it is given in this value, which is between 0 and 10. And so there is some fun. We let some jobs to fail. So we see in the error that in the queue that there are some errors as well. So let's start this consumer and look how it behaves. Make consumer consume simple. Okay. Now the consumer started to process message by message, because by default it's instructed to go one by one. When there is sleep 4, it will sleep for 4 seconds. And accordingly, when there is the different sleep value. And it will error when there is a sleep 0. We have 50 messages in the queue. In the monitoring right now, we can see that 45 are waiting, 1 is processing. We have just single consumer, so processing will be never over 1. Let's speed it up a bit. But I will show you before how the advanced consumer looks like. And it looks like this. The only difference in both consumers is the configuration of the consumer. The handler and the worker is exactly the same, but in this case, I am passing logger, and this is the crucial in our demo, because I am passing the parallel messages and configuring to 5. So it will not go one by one, but it will spin 5 concurrent consumers at a time. I can configure the log duration and polling interval, which was there in the diagram of the lifecycle. So I can tune how much often it will poll the database. But the with max parallel messages set to 5 is the crucial from the perspective of this demo. So let's run it. So make consume advanced built. And now you can see it is fetching 5 messages at the same time. Depending on the sleep time, it gets to another, but at most, it will be processing 5 messages at a time. We can see that it speeded up the processing of the queue. So right now, there are just 2 messages. Now everything is processed, or 2 are still being processed. Now it's okay. 4 of them out of 50 had 0 as the sleep value, so we log it as erroneous. So it was quite fast with parallelism. So let's publish one more so we can see how the consumer look like. Okay, we published. Of course, we can speed things up. We can consume advanced, run another one, and monitoring is telling us how many messages is there. Now we can see, because we have 2 consumers with parallel, both of them set to 5, so it's processing much better than before. Okay, so I will stop it. All the queues are processed, and the output of the monitor is the file which I can import in here. Import. It is this file. We'll replace this one. These are the data that are in the CSV file, and I will tell Google Sheets to insert the chart. And here I can very nicely see, it's my really basic monitoring tool, that since I started monitoring, there were 50 messages in the queue. Then I started the simple consumer. So the number of messages in the queue was decreasing. Here, at this moment, I started the advanced consumer. So it really helped. Then I was doing nothing for a while. Then I published some messages again. Meanwhile, before this query to get the length of the queue was executed, some of the messages were already processed by the advanced consumer. That's the reason why the line is not going to 50. And then, again, the tempo was exactly the same until this moment when I start the second advanced consumer, and then the processing is much steeper. The red line means how many consumers was there. So at the beginning there was just 1. Here I started 5 more, then I stopped, and then started 2 advanced, and so on. So this is the number of being processed messages, the red line, and the yellow line indicates how many errors are there in the queue. Everything what this is looking into is this simple table. So I can have a look that it changed. There will be some dates already filled, telling me when the message was processed. This is the query that I can insert the data into, so I don't have to have implementation of the PGQ publisher. I just can insert it via this query if I want. By this query, I can see whether there are some messages which are not being processed yet. It's empty, but if I run this query during the demo, there would be some, and we could see their log times. We can, of course, list all the messages which ended with error, which are these ones. They will probably have the same error because our handler is very simple. But what is very nice, that you can compute the average duration of your processing. So in average, it took 4.4 seconds to process the message, which kind of matches the Gaussian. And you can of course filter out, because the data of the messages are still in the queue until you delete them. So you can do the statistics like this, and you can extract all the payload, all the messages with payload where sleep was 9. So you can have a look. If you are debugging something or being curious about what is happening in your queue, you can look for the payload. So this was the demo, and I will continue with the presentation if I find the window. Oh, I hope it will start here. Replay. Demo. And finally, some recommendations how to use PGQ. The crucial way, or the crucial thing in order to have the consumer fast, is to keep the index that is there the index is there for the processed add field. By this, it distinguishes between the messages that need to be processed and between the messages that have already been processed, and ignore those. So if you really don't have strong opinion, just keep the indexes that are there and leave it there. But of course, the database is under your management, so you can do whatever you want to the table. If you want to add a field, you want some new field or modify whatever, it's your table, so you can basically. Always configure the options according to your consumer. So sometimes you are dealing with the long duration jobs, so probably the log duration should be longer. Sometimes you are sending emails, so log duration can be short. It depends on your concrete usage. The same with max parallel. If you are doing some memory extensive jobs like extracting the data as we do, we are very, let's say, curious if we can handle more than, let's say, 2, because if we hit 2 jobs that each requires 6 gigabytes of RAM, probably our Kubernetes pod will crash. But while sending emails, we can have max parallel configured to 10, because probably sending email, parsing some JSON will not allocate too much memory. So it depends on your concrete use case, and by observation, you can tune PGQ in order to match your needs. What we use in production is partitioning, because of course, as all the message data are being kept in the table or in the queue, sometimes you don't need them. We usually keep them for 90 days. Of course, this is a Postgres table, so you can back it up and have the access to all data if you wish. But in order to speed things up, in order to help the consumer, you can do the partitioning by day. And if you are curious, only in the messages, usually only the messages which are not processed are within the last partition. So the other partitions are there only to keep the historical data for our statistics, for our comparisons, and so on. And it's good to have partitioning in place. Of course, you can delete the old data, but if you run the delete command in Postgres, it's blocking, so it can affect your update and select queries and insert queries. And partitioning is quite nice, a nice tool how to improve the performance, whereas you keep the old data in the database as well, and you automate the deletion of the old data. Observe the queue size, because if you don't know how long your queue is, you don't know if something behaves badly. If the queue is growing, probably your consumer needs to speed up. So this is the indicator that tells you, hey, something's bad happening with your service. And of course, if you have alerts, you can automate it. As you have all the data about the processing, about the failures, why not use them for inspection of your bugs? Because you can create some nice views. What was the most frequent failures in your consumers, and these are the errors you can focus on when developing. And if you are using Kubernetes, you can use KEDA, which is the autoscaler for or advanced horizontal pod autoscaler in Kubernetes. And using KEDA, which has the Postgres scaler, it's a plugin, you can create a query to your Postgres table and say, I want this pod to turn off when there is no traffic. When the queue is empty, I don't want this pod to be existing. So Kubernetes scale is down to 0, and when there is something in the queue, the KEDA will know in some interval, and will scale up your service, and you can scale up your service according to the queue size and so on. The threshold configuration is really up to you. In the demo, I just showed a simple example when there was one publisher and or multiple consumers, and one queue behind in the middle. But let's say in Datadog, we have more complicated thing. Every service can act like consumer and publisher at the same time, so there can be some logic. In here, there are some triggers for our actions to happen. This is the PHP service with just some business validation. Then it determines whether it's extraction or write action, and then it passes the message or some job to the queue, to service in Go, which knows what to do with these jobs. When they are done, they just fill some results to another queue, which is again can be in different language, And you can chain the queues as your business needs. In real life, in Datadog in our case, we have, let's say, there was a writer, mentioned the writer service. In Kubernetes, we have 7 pods of writer. In each, there is with parallel configured to 3. So altogether, we have 21 consumers consuming the queue. In Grafana, we have this chart when we can see the peaks. The yellow lines are the peaks in the daytime. Here, if you look into the database, we can have a look at the partitions. They are being auto-removed from the oldest. And if we are dealing with some error, we can see the payload, what happened, what was the input to our service. We can simulate it again. We can have a look what was the processing time, the error detail, why it failed, and so on. There is the metadata field, which you can use for, you can consider it like HTTP headers for trash. So you can put some data which consumer does not need or does not require in order to operate, but the information nice to have that you can filter by in your queries to the database and so on. And of course, as I said, we have multiple queues, all of covered by alerts. So when we see, or when Grafana sees that some queue is getting bigger, it will probably wake up in the middle of the night. Some links that I've used and resources. So link to the PGQ. We will be very, very glad if you try it. We will be very glad if you have some ideas how to improve it, and if you use it, of course. Special thanks to Marialeta, from who I used all the Gophers in the presentation, even this. Here's the link for the PostgreSQL. If you are dealing with scaling, automatic scaling, and you are not okay just with the basic horizontal pod autoscaler implementation in Kubernetes, there is plenty of scalers like Postgres, files, whatever, Kafka, RabbitMQ. So a lot of implementations that enables you to scale your pods according to some metrics from the systems you use. Once again, this is the guy who is the brain of the project. I'm just the mouth. If you have any questions, I will try to answer it. Otherwise, it's the end, my friend.
If you have any questions, okay, yeah.
Hey, thanks for the presentation. For how many languages do you have library supporting?
Yeah, so far the open sourced one is the Go only, but we are using it in production for 2 years or so alongside with the PHP. So we have the PHP implementation as well, of course, which we want to make public as well. Probably I will write a Node.js implementation too, and others. We don't use other technologies in our stack, so it's kind of nonsense for me to maintain it if I don't use it. So currently PHP and Go will be, PHP will be there soon, Node.js probably later, and no plans for the others right now.
And let's say in Kafka there is a guarantee of ordering based on some kind of message key. Is there anything similar to that in this?
No. It was not the recommend or the request from our business perspective to have it ordered. There is only the limit clause, but you know, it can, if something is logged, then it will be retried later if the processing fails. So no, the order is not guaranteed.
Cool, thanks.
Thank you for the presentation. I have like 2 questions. The first is, how would you drop a message if you're using this particular implementation? And the second one is, looking at the overhead cost of probably cleaning up the database and all of that, how would you look at the adoption of this particular implementation let's say RabbitMQ already has some sort of mechanism of doing that already.
Yeah, thank you. I will start from the end. So as I said, we use the smallest instance that AWS provides. The CPU usage is about 20% in there, even though we are using it quite extensively from my point of view. So there is always room to scale up, let's say, in a way of acquiring the bigger machine. But so far, at the beginning, we didn't have proper index there, so it was burning. But since there are the proper indexes are set correctly, there is no problem with performance in our side, in our scale. However, we did not do any, let's say, extensive performance testing. We usually observe it. We run it in production. We observe it like how it behaves. And so far, there was no big problem, except the one that we were missing the index, which was our fault, basically. So Postgres itself is quite good in performance. Only limitation which we can have is number of connections to the Postgres, which is sometimes limited. But the number of pods and the consumers we have, we are not hitting the limits anyway. So far, no trouble. And I forgot the first question. I'm sorry.
The first one is, how do you approach dropping a message? Let's say you publish the message, but you don't want the consumer to actually consume it. You just want to get rid of it.
So if you publish the message, the publisher is just guaranteed that it appears in the queue, and then in the queue it waits for some consumer to take it. So unless you spin no consumer, the message will remain there unprocessed.
I mean, if you want to get rid of it, you don't want it to be processed.
You just delete it from the table. You can, or you can discard it. If you can, in your handler, you can write your own rules. So basically, there was unmarshalling. So if I cannot unmarshal it, it will return error. So it will remain in the queue with the error, unmarshalling error, whatever. And you can have whatever business logic you want in your handler to filter out the messages you are interested in and those which you are not interested in. So it's up to you how you implement it. The only constraint there, it must be valid JSON from the PGQ point of view. Everything else is on your implementation.
Yeah, thanks for the presentation. So my question is about semantics. So usually queuing systems provide some semantics on how you consume messages. So for instance, at most once, at least once, etc. In your case, what would that be?
We don't cover this directly in the PGQ, but of course, when parsing the message, or you can wrap the publisher and consumer, and they can act like they are comparing whether it's the payload is valid against some protofile or whatever. So you can parse it according to your needs, but the only constraint from the PGQ point of view itself is that it's valid JSON. Everything else is up to you how you do it.
So one of the potential advantages of using Postgres, a queue in Postgres, is maybe you can put something into the database and have it in the same transaction as putting it into the queue, right? So like you're putting it into the queue as predicated on some other action. Can you do that with your library?
I'll tell you how we evolved to use PGQ. We used to use RabbitMQ. It was working very nice. Because we are only developers, we have no ops in our team. So we used managed service, managed RabbitMQ in AWS. And then came the day when we were extracting some data for our customer, and it took 2 hours or so to extract the data. And then the RabbitMQ broker thought the client is dead because there was no ping. They considered us, our Go application, to being, let's say, killed or whatever. They didn't know. Understandable from the point of view of RabbitMQ. So we wanted to change this parameter, change the behavior of RabbitMQ, but it was managed service in AWS. There is parameter for that in normal RabbitMQ, but there is no such configuration parameter in AWS, which led us to the point that we had to redesign the whole platform we have or use another tool. So we were investigating which should suit our needs best. So we were considering Kafka, we were considering some other tools, and then we evolved in something like this because we don't need any guarantee on the order. We just need to persist it and be sure that it is being processed just once, concurrently, no concurrency by multiple consumers at a time. And the fact that it's stored in the database is just a bonus on the side that we can observe it and we can have a nice overview of what is happening there. But it was not the purpose, it is just the side effect. And but anyway, when we were using RabbitMQ, we were persisting the messages as well. So we are blocked. We were not using the memory version. We were using we were waiting for I/O in order to RabbitMQ persisted, and it was almost the same slow as we have now. But we have the special scenario that we don't need the big throughput. We just need to process messages. And in our case, if we process it now or within 5 seconds, it doesn't make any difference for us. So we just need something reliable. And if the email is sent now or 10 seconds or even 2 minutes later, it's not a big deal for us.
So basically treat it as a separate service. And
Yeah. And by switching from RabbitMQ to Postgres, we removed one service or one technology from our stack, so we don't have to maintain it. We don't have to even know about that something like this exists. So the developers are more happier.
Hi, we are also on RabbitMQ on AWS, and we went from raw EC2 to Amazon MQ, and we really struggled with the retry story. We had to set up separate queues, separate brokers, separate everything to do message retries in Rabbit. How could you use like PG cron or something to achieve retry with this, or how do you do retry here? Is it like a separate table? Is it a separate schema? How does that work here?
Yeah, there is a. I didn't mention the field because I didn't want to, but there is consume count field in the create table statement, which indicates how many times at most the message can be retried, which is again configurable parameter. Because what happened to us when we were using RabbitMQ, that we consumed the message, then it allocated too much memory, the pod blown. Nobody sent signal to RabbitMQ, and another pod or another consumer started to consume the same again. Then it blown, and it was rotating there again and again. So for this reason, the consume count is there. So we try at most by default 3 times, I believe it is. So when the consume count, because the consume count is being incremented at the very beginning when you consume during the update query, the consume count is being increased. So it is the prevention from rotating out of memory jobs. But let's say the more business retry mechanism, we solve somewhere else. We have some service called dispatcher, which is dispatching the jobs to be executed, and this service is responsible for when it knows whether the action should be executed or not, and if it should be, it failed before, it knows it, so it retries it and publishes it into some input queue at the very beginning. So we don't deal with the retries on the level of PGQ, but somewhere else. But BGQ itself contains the safe mechanism for OOMs and other failures, like when the broker doesn't send any signal that it failed.
We have to close this. Thank you, Tomáš, again.
Thank you very much. Thank you very much.